Software is essential to nearly every business operation today. From streamlining workflows to managing data and enhancing customer experiences, software enables businesses to automate processes, improve productivity, and stay competitive in a fast-paced market. This is Chapter 3 of a larger course titled Introduction to Information Technology, and besides an introduction itself, the overall course is designed to bridge the gap between technical IT concepts and their practical application in business operations. In this chapter, we will begin by understanding what software is and its fundamental role within IT systems. Then, we will take an in-depth look into operating systems and learn their key components. Next, we will briefly explore the various types of application software that are commonly used in business environments. We will then discover the benefits of cloud-based software solutions, also known as SaaS, for businesses. We will also understand how software applications communicate and integrate with each other through APIs, which enable interoperability between different systems. Following that, we will get introduced to basic programming concepts and explore their practical usage in the corporate IT world. We will then explore how non-technical users can create applications using low-code and no-code platforms. Finally, we will learn about the various steps involved in releasing new application software updates to business users. By the end of this chapter, you will understand the different types of software, their functions, and their role in business operations. Software is a set of instructions that tell a computer how to perform tasks, from simple calculations to complex operations. Unlike hardware, which you can touch and feel, software is intangible. It exists as code stored in memory. Software is broadly divided into two main categories: system software, which runs in the background to manage hardware and system processes. For example, operating systems, utilities, and drivers. And we have application software, which are programs designed for the end users to perform tasks. For example, word processors, web browsers, and business applications. Let's explore system software. First, we have the operating system. It is a collection of system programs that manage a computer's hardware and software resources. It serves as a bridge between the hardware and users, providing a user-friendly interface and an environment in which applications can run. Examples of popular operating systems include Windows, macOS, Linux, and Android. At the core of an operating system is the kernel, which acts as a fundamental layer responsible for managing system resources and enabling communication between hardware and software. The kernel operates in the background, handling critical tasks such as process scheduling, memory management, device control, and system security. Let's explore 5 functions of the operating system next. We will start with process management. A program is a set of instructions written in computer-specific language. For example, a Python script. Applications are built using one or more programs. They are designed for end users to perform specific tasks or functions. For example, Microsoft Word. A program or application becomes a process when it's executed. For example, when you open Notepad, it transitions from a stored program to an active process managed by the operating system. So, a process is managed by the operating system and executed by the CPU. As a process manager, the operating system ensures that processes execute efficiently, fairly, and securely while maximizing system performance and user experience. It balances competing needs from processes and hardware resources to achieve seamless multitasking and system stability. Next, let's go through the various stages a process goes through with the example of running a text editor application like Notepad. When you launch Notepad, the operating system performs several steps to create and load the process into memory. The operating system assigns a unique process ID. A process control block or PCB is created to store various information about the processes such as process ID, the process state, CPU registers, memory management information, and open file descriptors, which keeps track of all files and input-output streams currently in use by that process. The Notepad program's executable file is loaded from storage into the system's main memory, which is the RAM, short for random access memory. Shared libraries or dependencies required by Notepad are also loaded into memory. Once the process is loaded, it transitions to the ready state where it waits for CPU time. The figure on the screen shows the rest of the states that a process can exist in. The operating system scheduler determines which process gets to use the CPU based on scheduling policies like round robin or priority scheduling. Once the CPU is allocated to the Notepad program, the process transitions from ready to running. The CPU will now execute any instruction from Notepad, such as handling text input. To run multiple processes simultaneously, the operating system performs context switching. When the CPU switches from Notepad to another process, the operating system saves Notepad's current state in its PCB. The operating system then retrieves the saved state of the next process, such as Google Chrome, from its PCB and loads it into the CPU. This allows the CPU to resume execution from where the previous Google Chrome process left off. Through context switching, the operating system allows multiple processes to share CPU time efficiently, creating the illusion of simultaneous execution in a time-sharing system. And when the process needs to perform an input-output or I/O operation such as saving a file to a disk, it temporarily stops using the CPU and enters a waiting state. Once the I/O operation finishes, Notepad resumes execution. And finally, when you close Notepad, the operating system terminates the process. The operating system will free up the memory allocated to the process, remove its PCB from the process table, and release any resources such as open files and network connections. At this point, the process ceases to exist and the operating system ensures that system resources are available for other processes. When we talk about memory, we are referring to the physical storage space like RAM, where data and instructions are temporarily stored while applications are running. The memory management function of an operating system ensures that a computer's memory is used efficiently and securely. Without it, applications would interfere with one another, leading to instability and errors. The operating system organizes memory of running processes into different sections to serve specific purposes. We have code, data, stack, and heap. Let's explore these through an example of a Google Chrome application running as a process. Code is the part of memory which stores the instructions that tells the computer what to do. The operating system ensures these instructions remain secure and unaltered. So for example, the instructions to load a web page, handle keyboard input, or render graphics on the screen are stored in the code section. The data part holds fixed or semi-fixed information needed for the application to work. It stores things like initial settings or constant values. The operating system manages access to this data and ensures it is available when needed. So for example, Chrome's default settings like the homepage URL or bookmarks that don't change often are stored here. The stack is a temporary workspace for small short-term tasks that need quick access. It works like a stack of sticky notes. New tasks go on top and are removed in reverse order. The operating system automatically manages the stack, adding and removing items as needed. So for example, when you load a web page, the stack temporarily holds data about the web address you're typing or process related to rendering the page. The heap is a dynamic memory allocation area used for data that needs to be allocated and deallocated at runtime. Unlike the stack, this memory is not automatically cleared, it's managed as needed. So for example, the DOM or document object model of web pages, images, videos, and other dynamically created objects in Chrome are stored in the heap. The heap allows Chrome to handle many tabs and multimedia content simultaneously. While there are deeper complexities in how memory is managed during programming, this breakdown provides a foundational understanding of how the operating system structures memory. For most IT and system administration tasks, this level of abstraction is sufficient to grasp how processes utilize memory. So let's check out the functions of memory management in an operating system. First is process address space management. Each process is given its own address space in the RAM, ensuring that it operates independently without interfering with other processes. This isolation enhances security and stability by preventing accidental or malicious access to another process's memory. The CPU does not directly access physical memory, but instead it works with virtual addresses. These virtual addresses act as references, and the operating system, along with the Memory Management Unit or MMU, translates them into physical locations using page tables or segment tables. This mechanism is known as virtual memory management. Let's move on to segmentation and paging. To efficiently allocate and manage this virtual memory, the operating system employs techniques like segmentation and paging, which determines how processes are structured in RAM. Segmentation organizes a process's memory into logical sections such as the core segment, data segment, stack, and heap. These can be variable size blocks. This matches the way programs are structured, making memory allocation more intuitive for programmers. And the link between the logical and physical address is maintained by the segment table, which tracks the range of addresses. However, segmentation can lead to external fragmentation over time, where free memory becomes scattered, making efficient allocation more difficult. Paging, on the other hand, divides memory into equal fixed size blocks to optimize allocation and prevent fragmentation. The operating system maintains a page table that maps logical pages used by the process to physical frames in the RAM. Paging eliminates external fragmentation, as any free frame can be assigned to a process without worrying about varying segment sizes. This provides a more efficient utilization of RAM. Modern operating systems use a combination of both these techniques. Let's move on to virtual memory. When physical RAM is insufficient, the operating system extends available memory using virtual memory. It achieves this by swapping inactive memory pages from RAM to secondary storage, freeing up space for active processes. And when needed again, these pages can be loaded back into RAM. This allows the system to run more applications than the physical RAM alone would permit, but this comes at the cost of performance since disk access is slower than RAM. Then we have allocation and deallocation. Memory must be assigned to processes as they execute and released when they terminate. The operating system dynamically manages allocation, that is, assigning memory to a process when it starts or when it requests additional space, for example, expanding the heap, and deallocation is the releasing of memory back to the system when a process terminates or no longer needs it. Efficient allocation prevents memory leaks, where memory remains allocated even after a process is done using it. Then we have file system management. A file system is a method used by the operating system to store and organize data on storage devices. It provides a logical structure to access physical storage, making it easier to locate, read, write, and update data. Without a file system, data placed in a storage medium would be one large chunk of data with no way to tell where one piece of information stops and the next begins. Different operating systems use different file systems. Some common file systems include FAT or FAT, which is the file allocation table used in older systems and portable storage devices like USB drives. NTFS, which is a new technology file system, is used by Windows for better security, large file support, and efficient space utilization. HFS Plus and APFS is used by macOS for advanced features like cloning and snapshots. ext4, or the fourth extended file system, is commonly used in Linux systems and is known for its robustness and performance. Let's look at the structure of a file system. A file system typically organizes data in layers. We have files, which are basic units of storage containing data, for example, a document, image, or video. Then we have file metadata. Metadata includes information about a file such as its name, size, type, permissions, and creation and modification dates. There are directories or folders, which are a collection of files organized in a hierarchical structure. For example, we can see the following file path, which includes the directory and the file name. Partitions are divisions on a storage device, each acting as an independent logical storage unit. So for example, we commonly have C and D drives on a Windows system, and we have the FAT or similar structures, which is a map maintained by the OS to track where files are stored on the disk. In addition to organizing and storing files, the operating system manages file permissions and access controls, ensuring data security and user privacy. It also handles file operations such as creation, modification, and deletion, and prevents conflicts when multiple processes try to access the same files. Then we have the user interface. In the context of the operating system, the user interface or UI allows users to interact with the computer's hardware and software. Let's look at the different types of UIs. We have the graphical user interface or GUI, also known as a GUI. A graphical user interface allows users to interact with the computer through graphical elements such as windows, icons, menus, and buttons. So for example, we have the Windows OS, Mac OS, and Linux distributions with GUIs such as Ubuntu. And we also have a command line interface or CLI, which allows users to interact with the computer by typing text commands into a terminal or console. It features commands, which are specific instructions typed by the users to perform tasks, and prompt, which is a symbol or text indicating the system is ready to accept commands. Examples would include Windows Command Prompt, macOS Terminal, and Linux Shell such as Bash. Let's move on to security and access control. Security ensures data and system integrity, while access control defines who can access which resources and what actions they are allowed to perform. The OS uses several mechanisms to implement security and access control. User authentication verifies the identity of users through methods like passwords and biometrics. User authorization determines what authenticated users can access and do, often using role-based access control or RBAC, which assigns permissions based on roles such as a student or admin. Data encryption secures data by converting it into a coded format that unauthorized users cannot easily understand. For example, full disk encryption can protect your data even if someone physically steals your laptop. Privilege levels control the access each user has. When you try to install a new program on a computer, the OS may require you to enter an admin password to grant you elevated privileges to complete the installation. Security policies define rules for maintaining security, such as requiring strong passwords or locking accounts after multiple failed login attempts. And firewalls monitor and control incoming and outgoing network traffic to block potential threats. Okay, that was a deep dive into operating systems. Now, let's return to the software categories. We also have another subcategory called device drivers, which act as translators between the operating system and hardware devices like printers, external monitors, and storage devices. The OS relies on these drivers to communicate with the hardware, sending and receiving instructions in a language the device understands. Without the right drivers, these devices wouldn't work properly, leading to compatibility issues, performance problems, or complete device failure. So for example, when you plug in a new mouse into your computer, the OS detects the device, loads the appropriate driver, and enables functionality, allowing you to move the cursor and click without any manual configuration. Firmware is a type of system software that provides low-level control for hardware devices. It is embedded directly into hardware components and enables them to function as intended. Unlike regular software, firmware is not meant to be frequently changed and is essential for basic operations of the devices. It is found in computers, embedded systems, and consumer electronics. So for example, the firmware in a smart thermostat controls temperature settings and communicates with sensors to regulate heating and cooling. Let's move to the next branch, which is application software. Application software helps businesses perform specific tasks and streamline operations. While traditional classifications group software based on functionality or architecture, we will focus on categorizing software from a business perspective, which is more relevant to organizations' needs. Let's look at the key types used in business environments. We have business critical applications. These include enterprise resource planning or ERP systems such as SAP and Oracle, which integrate core business functions like finance, HR, and supply chain management into a unified platform. We also have productivity software. These are tools like Microsoft Office, Google Workspace, and project management applications such as Trello, which help teams collaborate, manage documents, and track tasks. Then there is business intelligence or BI and analytics software. Solutions like Power BI and Tableau enable organizations to analyze large data sets, visualize trends, and gain actionable insights. We have customer relationship management software or CRM software. Platforms such as Salesforce and HubSpot help companies manage customer interactions, track sales pipelines, and enhance customer service. And lastly, we have communication and collaboration tools. Software like Microsoft Teams, Slack, and Zoom facilitate remote work, real-time collaboration, and team connectivity. In the past, businesses used locally installed software, meaning the program was installed directly on an individual computer or a company's internal servers. For example, if you installed Microsoft Excel on your desktop, you could only use it on that specific device. Now, businesses are moving to cloud-based software also known as software as a service or SaaS. This means the software runs on remote servers and you can access it over the internet instead of installing it on a specific machine. For example, Microsoft 365 allows you to open Excel from any device, collaborate in real time, and access the latest version without manually updating the software. So in this case, the actual Excel application runs on Microsoft's cloud servers, which we can access from any device with an internet connection. Businesses prefer cloud-based software because employees can work from any device with an internet connection. The software provider ensures everyone is using the latest version. No need for companies to buy and maintain powerful computers to run the software, and easily add or remove users as the business grows. This shift to the cloud helps companies stay flexible, reduce costs, and improve collaboration across teams. Okay, let's move on to understanding APIs. Imagine you're ordering food through a delivery app like Uber Eats. You select a restaurant, add items to your cart, and place the order. But what happens behind the scenes? The app doesn't store restaurant data itself. It uses an API or application programming interface to connect with the restaurant system. The app sends a request to check if your selected items are available. The restaurant system responds with the confirmation, and the app then shows your estimated delivery time. APIs work the same way in business. They allow different software systems to talk to each other. For example, an e-commerce website can use an API to automatically update stock levels from a warehouse system. There are different types of requests. A GET request retrieves data, such as checking stock levels, while a POST request sends new data, like placing an order. The system then responds with the relevant information. The response includes a status code to indicate whether the request was successful or if there was an issue. Some common response codes include 200 for OK. This means that the request was successful and the server returns the requested data. 400 means that it was a bad request, which means the request was malformed or missing required data, so the server can't process it. And 500 stands for internal server error, which means something went wrong on the server's side and it can't process the request. So for example, if an online payment fails due to incorrect card details, the payment system might return a 400 error indicating a bad request. If the payment service itself crashes, a 500 error would be returned. APIs make business operations smoother by reducing manual work, improving efficiency, and ensuring real-time updates. That's why businesses rely on APIs to integrate systems like CRM, finance tools, and e-commerce platforms seamlessly. A program is simply a set of instructions written as a code that tell a computer what to do. Think of it like a recipe. You provide step-by-step directions and the computer follows them precisely. These instructions are written in a programming language, which is a structured way to communicate with computers. Programs are written in special tools called code editors or IDEs. These are like advanced text editors designed for coding. Examples include Jupyter Notebook for Python or SQL Server Management Studio for SQL. Once the code is written, it needs to be executed. Some languages are interpreted, which means the computer reads and runs them line by line, making them flexible, but often slower than compiled languages. Examples include Python and JavaScript. Compiled languages require system software called a compiler to translate the entire code into machine code before execution. Examples include C and C++. And some languages use a hybrid approach. Code is first compiled into an intermediate representation like Java bytecode, which enables cross-platform execution, and is then interpreted or further compiled at runtime. Examples would include Java and C#. But how is code executed in the backend? Let's tie this back to our previous session on hardware. The code file is first saved in storage, either as a script for interpreted languages or as a compiled executable for compiled languages. When executed, it is loaded into RAM for fast access, and the CPU processes its instructions to perform tasks and generate output. It is not always necessary to know how to actually write code. In the event that you need to communicate a requirement, you can use pseudocode, which is a simplified way to describe programming language using plain language. Programming is built on logical constructs that help automate tasks and process data efficiently. We can use pseudocode to represent each of the following constructs. Loops allow us to repeat a task multiple times without writing the same instruction over and over. For example, if we want to print the numbers from 1 to 5, we can use a loop. So here on the screen, the loop starts at 1, increments by 1 each time, and stops at 5, printing each number along the way. Conditions help us choose between different actions based on a given situation. Let's say we need to check whether a number is positive or negative. The program on the screen checks the value of the number. If it is greater than 0, it prints positive. Otherwise, it prints negative. Functions allow us to reuse code efficiently by grouping related instructions into a single unit. So for example, if we frequently need to calculate the square of a number, we can create a function as we can see on the screen. So instead of writing number times number every time, we can just call square of 4 and it will return 16. Functions help keep programs structured and maintainable. While computer science focuses on developing new algorithms, data structures, and system architectures, IT programming is practical and business-oriented. IT professionals use programming primarily for automation, system integration, and process optimization rather than developing entirely new software applications from scratch. IT programming revolves around two key concepts. Functions, as you have seen previously, these are small reusable blocks of code that perform a specific task. Common languages used to write functions include Python, JavaScript, C#, and Groovy, which is an offshoot of Java. And we also have scripts, which are a sequence of commands that can automate administrative and operational tasks. Common languages used to write scripts include Bash, PowerShell, and Python. In IT, functions play a crucial role in various scenarios, including middleware is software that connects different applications, enabling data exchange and communication between them. For example, MuleSoft, Delboomi, or Apache Camel. So, a legacy inventory system might output data in a CSV format, while a modern e-commerce platform requires JSON. So, an integration developer can write a custom Java function within Apache Camel to parse the CSV, transform it into JSON, and then route it to the e-commerce platform, ensuring seamless data flow. Modern cloud platforms enable businesses to run event-driven functions without managing infrastructure. This setup is known as serverless computing. For example, Azure Functions, AWS Lambda, and Google Cloud Functions. For instance, a cloud engineer can use Azure Functions to trigger small scripts in response to system events, such as a file being uploaded, an HTTP request, or a database update. We can also use functions to manipulate API requests and responses. For example, using JavaScript within an API testing tool such as Postman, functions can also be embedded into IT management tools. For example, a network administrator can use Python functions within a monitoring tool like Zabbix to analyze network traffic patterns. Scripts automate common IT tasks, saving time and reducing human error. Let's look at some use cases. Let's look at system administration. So for example, a system administrator can use PowerShell scripts to automate the process of onboarding new employees. We can use scripts to manage cloud resources. So for example, a cloud engineer can use Bash scripts to manage cloud infrastructure. Let's look at some more examples. So a security analyst can use Python scripts to parse server logs. For example, a Python script can scan web server logs for suspicious activity, such as repeated failed login attempts or unauthorized access attempts. Let's look at an example in database maintenance. A database administrator can use SQL scripts to automate tasks such as database backups, cleanup, and reporting. And let's see one example in the field of DevOps. A DevOps engineer can use scripts within Azure DevOps to automate software deployments. The Azure DevOps pipeline itself can be defined using YAML, and the infrastructure it deploys can be defined using Bicep. While scripts and functions empower IT professionals to automate tasks and integrate systems, a parallel trend is democratizing software development for a broader audience. Traditionally, building software required coding skills and IT involvement. However, low-code and no-code platforms now allow business users to create applications without deep technical knowledge. With low-code platforms, you may need minimal coding for customization. Examples include Microsoft Power Apps, Mendix, and OutSystems. These are great for business applications that require some complexity but don't need full-scale programming. No-code platforms like Zapier, Airtable, and Microsoft Power Automate let users build applications and automate workflows without any coding at all. While these platforms accelerate development, they may have limitations in flexibility and scalability compared to traditional coding approaches. A sample workflow is shown on the screen. Here we are extracting daily sales data from a database and sending it to the app on a salesperson's tablets via an API. Low-code, no-code workflows are typically represented using shapes and connectors. Visually, they represent a typical flowchart. Each shape represents a specific function, such as applying conditional logic or retrieving data from a database, while arrows define the logical flow between these steps. As a developer using low-code, no-code platforms, the key tasks involve selecting the appropriate shapes, configuring them with the required parameters, and linking them with connectors until the workflow achieves its intended outcome. An application software release refers to the process of making a new version of a software product or system available for use. For this exercise, we shall focus on a business-facing software where the business and IT functions are the key stakeholders. So an application software release from this perspective could involve launching a new CRM tool, an upgrade to a newer version of an ERP, or an improvement to an existing solution such as minor updates every quarter. Critical releases follow a structured release cycle to ensure everything runs smoothly. First, let's talk about the key teams involved. The project owner ensures the update meets business needs. We have SMEs or subject matter experts who provide insights into how the software should work in daily operations. There are BAs or business analysts that translate these needs into technical specifications for developers. IT developers can be either in-house or consultants who build and test the changes. And project managers oversee the entire release, ensuring deadlines and budgets are met. Now let's look at the software release cycle. First, we have development. So developers create and build new features or updates in the software. During this phase, the development team also conducts initial testing, often referred to as unit testing, to ensure that individual components work as needed before moving on to larger tests. Then we have QA or quality assurance. After development, the QA team takes over. They focus on more comprehensive testing such as functional testing, regression testing, and performance testing. QA verifies that the software behaves as expected, identifies bugs, and ensures overall quality before the software moves on to the next stage. This brings us to the SIT stage, which stands for System Integration Testing. This phase ensures that the new version works seamlessly with other systems in the business environment such as finance, HR, or supply chain modules. It checks for any compatibility issues between the new software and existing systems. Then we move on to UAT or User Acceptance Testing. In this stage, business users test the software in a controlled environment. They confirm whether the software meets their requirements and business needs. If the users approve the software, the update moves forward. And we have the production release. The final approved version of the software is deployed and made available for live business use. A well-managed software release ensures that business operations remain smooth, secure, and efficient while minimizing risks. Okay, that brings us to the end. To wrap up, here are the key takeaways from today's session on understanding software and its role in business operations. Software enables businesses to perform tasks efficiently, streamline operations, and improve productivity. System software keeps hardware running, while application software helps users perform specific tasks. The operating system manages processes, memories, files, user interfaces, and security for smooth computing. Cloud-based software offers flexibility, cost savings, and remote access, making it ideal for modern businesses. APIs allow different software systems to interact, improving efficiency and enabling seamless integrations. Software is built using code which instructs computers on tasks from simple to complex operations. IT programming uses scripts and functions for automation and integration. Low-code and no-code platforms let business users create applications without extensive programming knowledge. And application software releases involve development, testing, and deployment phases to ensure quality and meet business needs.